Welcome back. So we have quite a few people out right now, so we'll keep going with these videos. I don't know if anybody's watching them. I don't know what happened. Something glitched on the one on Friday, so I'm still trying to figure out if I can upload that one. But hopefully they'll be up and running. Okay, so let's finish up chapter 4, then we're going to do a worksheet today on chapter 4, make sure we're up to speed with working with atomic symbols. A couple things with the anatomy of the symbol. When we look at the periodic table, of course, we can tell a lot from the red and the blue. So we need to be able to work today by the end of today, be able to be pretty comfortable with what these two numbers are right here. One of the things we're not going to work with in this course is working with the mole ratio. Avogadro's number, some of you that have had other form of chemistry know that Avogadro's number 6.02 times 10.3 molecules or atoms or whatever per mole. We're not going to work with that. We don't do stoichiometry in here. Right? We don't balance chemical equations. This is really a class built on understanding carbon and its interaction with building systems of the body and different molecules that we work with in medicine. Okay? So we do have to have a working knowledge, though, of the anatomy of the symbol on the periodic table. So here's the thing. Oftentimes, we're not told the whole story. There are actually 4 locations on an atomic symbol. Excuse me. There's 4 locations. There's a location here, a location here, there's actually a location here, and there's also a location here. Okay? So on any symbol, as a chemist, we have 4 different places that we typically think of working with these atoms, if you will. Okay? This is the atomic symbol, or the atomic number here. Okay. This is the mass number up here. Okay. This up here is the charge of the atom. And so, if I'm just talking about something like zinc looks like that. We typically, when it's a zinc metal, we don't have anything up here. Sometimes you might see, if it's a metal, you actually might see a 0 up there, and that's what it represents. It means it's in its elemental form. Okay, it has all of its electrons, hasn't lost electrons, hasn't gained electrons. Okay, so we'll see that. And down here, man, frog in my throat. Down here is going to be it's really our stoichiometry number, but it's the number of atoms in formula. Okay, and again, that's one that if you have something like water, H2O, you can see that there's a number down here. All right, that number tells me that there are 2 hydrogens for every 1 oxygen. And if I have a 1 there, I just imply it so I don't write that. So if I do something like glucose, glucose is C6, H12O6. Okay? So in that symbol, I know that there's 6 carbons, 12 hydrogens, 6 oxygens. Okay? So that's how we work around the atomic symbol in all 4 locations, and they can become very important throughout different types of chemistry. Stoichiometry, oxidation reduction would be if I lose my electron to become zinc 1 or zinc 2, then I'm going to be a positive and be a cation. We'll talk about that in chapter 6. Up here is where we're going to be for today. My atomic number, in this one, it's the blue one up in the box. Okay, that's my atomic number. And as you'll remember last week, I talked about how chemistry is really not that complex. We're just counting from 1 to 118. Okay, that 1 to 118 goes here. That's my atomic number. All right? So, for example, something like carbon, one of the ones we want to be really familiar with by the end of this semester. Carbon, a typical carbon atom, is going to look like this. All right, now that tells me quite a bit. And this also gets into what we would call as the isotopes, isomers of carbon. All right, so carbon 12 I should say, carbon 12 with 6 neutrons. This is the atom which standardizes the periodic table. All atoms on the periodic table are standardized to carbon-12, okay? Carbon-12 is exactly 12.00000 forever. Atomic mass units or grams per mole if you're working with laboratory level of chemistry, okay? Because the periodic table is standardized at carbon, you'll see up here that carbon is not 12.0000000, it's 12.011. Why? Well, that's where we have to get into this thing called isomers. So, when I look at this carbon 6 tells me it's carbon, 6 protons, 6 electrons, in this case 6 neutrons. My mass number is the number of protons plus neutrons. Okay? Whereas my atomic number is the number of protons. And electrons, if element is in ground state. Okay? So if the element or the atom is in its ground state, then that number is also the number of electrons. All right? But typically we're working in here with cations and anions, so we're not really working with electrons in their ground state. We're moving electrons around. All right? So this number of protons, minus this number of protons plus the number of neutrons gives me what? 6. It gives me the number of neutrons. So carbon-12 has 6 protons and 6 neutrons. Okay? There are 2 other isomers, or isotopes, of carbon. You have carbon-13, carbon-12, and you have carbon-14. Some of you probably have heard of carbon-14, carbon-14 dating. Carbon-14 is not a stable isotope. Carbon-14 decays to nitrogen. All right? So carbon-14 decays to nitrogen. So the way that this actually works is kind of interesting. As long as the sample is living, it's influxing carbon at a set ratio. Once the organism dies, these 2 are stable, this one begins to decompose. Okay? And so if we look at the ratio of what we think it was when the animal was alive versus what we know it to be today, we can get an approximate date of that. All right? And the caveat with carbon-14 dating is the sample has to have once been living. You cannot carbon date rocks, shells, layers of soil. You have to carbon date something like a tree or a papyri or a shroud of Turin or something like this, okay? And we can go back and look at that carbon ratio and see what they are. But here's the thing. How many neutrons does carbon-13 have? How do I know that? Because 13 minus 6 equals 7. Okay, how many neutrons does carbon-14 have? 8, okay? So here's the way this actually works. Here's why you don't have 12.011 up there. Carbon-12 is the elemental abundance of 98.89%. Most carbon that we have within glucose, within the body, within organisms, excuse me, is carbon-12. Carbon-13 is about 1.11%, okay? Carbon-14 is real small, about 0.005%, not a whole lot in it to start with. So we really don't bring that into the equation. So in order to calculate what an average carbon would weigh on the surface of the Earth, we would take 98.89% times 12, 1.11% times 13. We add those together, and if you look, it becomes 12.011, okay? So that's why that number there is not an exact number, like this number is exact, okay? And so if you look at the periodic table, look at nitrogen. Nitrogen's gonna be pretty much N15, isn't it? Or excuse me, N14. Okay, and it should be 14. It is, it's pretty good, pretty close. So not a lot of isotopes. Probably can predict which isotope is in more abundance.
nitrogen 14. There's probably going to be a little nitrogen 15 floating around because that's why it's going to be bigger than 14. Whereas over here with oxygen, notice, oxygen should be 16, right? It's not. It's a little bit less than 16, which tells me that oxygen 16 is probably the most abundant, but there probably is a little oxygen 15 floating around, and I know that to be true because we can use that in the organic lab as a tag on certain molecules, okay? So you can see that that's why these are skewing away from. Now, one of the other things that you want to notice, for us it doesn't really matter because we're moving into organic chemistry real soon, but for the most part, you should have about 1-to-1 neutron to proton. So it should be about 5 to 10, 6 to 12, 7 to 14, 8 to 16, 9 to 18. See how that works? 10 to 20. But as you get bigger and bigger and bigger, as the atoms begin to grow, the thought is the strong binding force in the nucleus needs more neutrons to separate out those protons, so we begin to have more neutrons in the nucleus for the stable isotopes. And so that's why something like lead you'd expect it to be about 164, and it's 207, meaning it's got a lot more neutrons in there. So we call this actually dechem, we call this the delta stability. It begins to move more into the neutrons to stabilize the nucleus, okay? But thankfully for us, most of what we do is above this line, okay? So we don't really have to worry about that ratio down there. Okay, any questions on this? Because the worksheet's gonna have several of these on there for you to enjoy. Okay, good, ish. Okay, the last thing we want to talk about before we move on in and finish this chapter and work on our in-class worksheet, we want to talk about periodic trends. The most important trend that we'll deal with is electronegativity. That's next chapter. So for now, the trend that we typically see with the periodic table is this. As I go down the periodic table, I'm adding more mass. I'm adding more electrons and protons and neutrons to the atom. It should make intuitive sense that as I go down the periodic table, I'm going to have to get larger in order to put those electrons and protons in. Okay, so that's just a trend we see. We don't see exceptions to this. Hydrogen is going to be smaller than lithium, which is smaller than sodium, which is smaller than potassium, rubidium, and cesium. Okay, it goes down. So it's increasing in size as we go down. Where it's a little bit weird, you just have to memorize this, and there's a reason for it. It actually gets smaller as we go from left to right. Okay? That might be a little counterintuitive, because you're still getting bigger, right? If you look at this, boron has 5 protons, carbon has 6 protons, carbon's slightly smaller than boron. And the reason for that is what we call the Z effective charge of the nucleus. It actually is sucking in these electrons more. So carbon sucks in the electrons more, nitrogen sucks them in more, oxygen sucks them more. When you get to neon, it's a pretty small molecule, or it's a pretty small atom. Okay, so bigger from top to bottom, smaller from left to right, or bigger from right to left, okay? Well, that's the trend. As far as charge, I talked about this a little bit last week. Lithium and sodium, potassium, rubidium, cesium really want to look noble because the noble gases sit here. So it's going to be fairly easy for rubidium to lose an electron. It really wants to be Rb+. Strontium wants to be Sr2+, 1, 2. I will come back to that in chapter 6 when we actually start to make compounds. Okay? When we start to talk about things like cesium nitrate, cesium acetate, calcium phosphate. We're going to get into nomenclature and be able to speak the language of general chemistry. Okay, so I'll talk about cations and anions and polyatomic anions in chapter 6. All right. The big takeaway from chapter 4 is understanding what an atom is, being able to use the periodic table in a practical way that can actually work with these atoms and these elements. Okay, to know my way around the symbols and what each of those categories means, be able to count number of protons, be able to talk about isotopes, be able to talk about some of the periodic trends, which I'll come back to in chapter 6, and to be able to work with, basically just work with elemental symbols, okay? And that's about it. One of the things that might not be super straightforward is the energy levels, the quantum levels. Just remember they're up here if you need a little help. 228, 288, 288, 18, 28, 18, 8. Okay? So on our exercise, these are the numbers that we're looking for when I talk about the electron configuration. All right, we're gonna use these, not the 1s22, S22P stuff that I would use in the general chemistry course. Okay, any questions on chapter 4? Feel like you're mastering it? So these are good little ways to say, do I really know chapter 4 well enough to move on? If not, where do I have to go back? Where do I have to go back and do a little work? Maybe I need to get a little help. So you're free to work with these, work with someone next to you if you want. If you want to do it by yourself, that's cool. But this is just a way to kind of, if I were to give a quiz, this is what it would look like. All right? So I'm not giving you a quiz, I'm giving you a worksheet. So it's kind of like an open note, open brain. Someone asked me in email if our exams in here are open notes, and the answer is no, they are closed notes. So I really do want, I'm not a big fan of memorization, but I am a fan of base knowledge. Base knowledge, so.